which I'll show you in this little movie. And I think we're linked up to the audio. So it's going to be a little noisy, but that's quite deliberate. So let's see if I can... You see, it's noisy even before it starts. And I'll advance this a little bit. I'm just... You can even hear me whispering. Many of you may have seen this phenomenon before. Rotating disk, that's all it is. It's actually rotating on its rim. It's precessing rather rapidly. You see the frequency is increasing. Well, that is a finite time singularity. There's no question about it. We're all very interested in the phenomenon, the possible existence of finite time singularities in fluid mechanics. And this is really why this phenomenon attracted my attention. And the immediate question is how actually, well, one question, there may be many others. You see, if you consider that problem as a problem in ideal analytical dynamics with no dissipation, then it will precess like that forever. Forever. I think Euler knew that. Can't find it anywhere in his writings, but I'm pretty sure he could solve that problem. But as soon as you have a little dissipation, the whole thing changes. Firstly, it seems to precess more and more rapidly, which is strange for a start. The note, the sound, the frequency goes up. And secondly, you have this finite time singularity, so utterly different from the ideal situation. And that's caused by dissipation. Something is dissipating the energy. And the question is what? Well, I naturally, being a fluid dynamicist, I thought the thin film of air between the disk and the substrate being jiggled back and forward very rapidly is dissipating energy by viscosity. Admittedly very weak viscosity because it's air, but still, what else? However, that's extremely controversial. That was my answer at the time in the year, I think it was 1999, hotly disputed. The alternative that's put forward is solid rolling friction. A slight deformation at the point. It's not really a point of contact. It's a little area of contact. So it becomes a very, very difficult problem, I think, in solid mechanics. Then the next one, the rattleback, or CELT, as its technical name. And this is the Cambridge University CELT, as you see. University of Cambridge, the CELT, little canoe-shaped object. It doesn't like rotating in the clockwise direction. Watch this carefully, try. It doesn't like it. It reverses. It reverses. Now you try the other way. I think you try the other way. Try the other way. Anti-clockwise. Well, it's pretty happy. Actually, if you look very closely, you see the little reversal at the very end. A little reversal, but not nearly so violent as the reversal going the... So there's the bad way, which is that. And then there's the good way. And you must ask yourself, well, why is this? This object looks just like a little canoe. Why? What's going on?
The Mystery of High-Energy Cosmic Rays. Presented by Science at NASA. Hold out your hand for 10 seconds. A dozen electrons and muons just zipped unfelt through your palm. The ghostly particles are what scientists call secondary cosmic rays, subatomic debris from collisions between molecules high in Earth's atmosphere and high-energy cosmic rays from outer space. This daily shower, which never stops, is a sign of violent events in deep space. It's believed the majority of cosmic rays come from supernova explosions. When massive stars explode, they blast most of their material into space. The expanding shock waves can break apart interstellar atoms and accelerate the debris to unimaginably high energies. Other unknown cataclysmic phenomena may be at work too, especially for the most energetic cosmic rays. Unsolved, a professor of physics at the University of Maryland, says, cosmic ray particles with energies as high as 10 to the 20th power electron volts have been measured on the ground. This is more energy than we have achieved in the most powerful man-made particle accelerators. But how do natural cosmic ray accelerators pump so much energy into these particles? This is one of the biggest mysteries in astrophysics. While indications of the energies of cosmic ray particles can be measured from the ground, Saab and colleagues have taken their study to higher elevations, directly measuring particles from space before they break up in Earth's atmosphere. The cosmic ray detector known as CREAM, the Cosmic Ray Energetics and Mass Investigation, has been launched to the stratosphere above Antarctica on board long-duration helium-filled balloons. By lofting the detector above 99% of the Earth's atmosphere, researchers get a better idea of what cosmic rays are like before they collide with nuclei in the air above the detector. CREAM is able to measure the energy and direction of each incoming cosmic ray particle and identify the particle type by measuring its charge, thereby providing clues to the particle's origin and acceleration mechanisms. Since 2004, the team has flown CREAM 7 times over Antarctica, accumulating more than 191 days of data from altitudes as high as 120,000 feet. They're about to go even higher. CREAM is heading for space. A reconfigured CREAM detector is scheduled to travel to the International Space Station in 2017 aboard SpaceX's Dragon spacecraft on a Falcon 9 rocket. Named ISS CREAM, it will remain installed on the Japanese experiment module, also known as Kibo, for at least 3 years. SAW says the ISS provides an excellent monitoring platform for high-energy cosmic rays. The station allows for long-term monitoring in lieu of multiple limited-duration balloon flights, providing direct, unimpeded access to incoming cosmic rays without atmospheric interference. The longer exposure times on the space station allow for the measurement of higher energies. ISS CREAM has a goal of measuring the highest energy possible for direct measurement of high-energy cosmic rays. She adds, the mysterious nature of cosmic rays serves as a reminder of just how little we know about our universe. For more high-energy science from beyond Earth's atmosphere, stay tuned to science.nasa.gov.
At any given moment, about 1,800 thunderstorms are in progress somewhere on the globe. New observations by NASA's Fermi Gamma Ray Space Telescope show that thunderstorms make antimatter. The process starts with a terrestrial gamma ray flash, or TGF, an intense pulse of gamma rays originating from thunderstorms. These dots mark TGFs observed by Fermi's Gamma Ray Burst Monitor during the spacecraft's first 8 months of operations. Researchers estimate that there may be as many as 500 TGFs each day. On December 14, 2009, as Fermi passed over Egypt, it spotted a TGF produced by a thunderstorm in Zambia. The TGF was over the spacecraft's horizon, where Fermi couldn't see it. So how could Fermi have detected it? Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays. The spacecraft has observed this phenomenon on at least 4 other occasions. So the next time lightning flashes and thunder roars, remember, you may be witnessing antimatter in the making.